Assalamualaikum warahmatullahi wabarakatuh and greetings. We continue our lesson with chapter 6, which is Laplace and Poisson's. Basically, this is the shortest chapter for EMT. We will cover three things. The first thing is the uniqueness theorems. Second is the Poisson equation. Lastly is the Laplace equations. The objective for the chapter is first to understand the concept of uniqueness theorems. Second, to calculate the electric potential or electric field intensity at a given point using the solution of Poisson or Laplace equations. Right, knowing the boundaries and the property of the dielectric material, we can find the electric field intensities, surface charge density, capacitance, and energy. That's why I am telling you before that the capacitance is more important in these chapters. Right, so we will having the boundaries and also the region where we want to solve it. For example, I have coaxial cable, and then I want to find out what is the capacitance for the coaxial cable. So we have to use whether the Laplace or the Poisson equation in order to solve the problems. Next, let's see the overview of what we have learned in the previous topic and what we will learn in this topic. We have a different charge distribution, such as we have whether the point charge, line charge, surface charge, and volume charge. From the different charge distribution, we can find the electric field intensity by using whether the Coulomb's law or the Gauss law, depend on the case. For example, if you have the finite structures, so we can use the Coulomb's law. If you have the symmetrical charge or the infinite charge distribution, you can use the Gauss law to find the electric field intensity. Next, in chapter 4, we already learned how to find the potential for the different case, whether it's a point charge, surface charge, and so on. Right, so we can relate the potential with the electric field intensity by using the potential gradients. Okay, this is what we have covered in the previous chapters. But in this chapter, we will find first the electric potential by using the uniqueness theorems, and then the boundary condition, and we have the area properties where we want to do the analysis. This is one of the most important thing in these chapters. Okay, you will be introduced with what is a Laplace and Poisson equations. From the first Maxwell equation, we have the divergence of T equal to rho v. From these expressions, okay, D is equal to epsilon E. Consider the homogeneous material where this epsilon is considered as a constant. So we can bring out from these expressions, and then we can relate the E with a V, where E is equal to negative gradient of V. So as a conclusions, we can derive the Poisson equation, which is the Laplacian of V is equal to negative rho V divided by epsilon. And this Laplacian is based on the coordinate system, whether you are dealing with a Cartesian, cylindrical, or spherical coordinate. Let's say when the right hand side of the Poisson equation becomes 0, where we don't have the charge density in our system or in our region, so we got del square V is equal to 0. This is known as the Laplace equations. Refer to these expressions. Del square is referred to the Laplacian operator. The Laplacian operator can be Cartesian coordinate, cylindrical coordinate, or spherical coordinate. And in each coordinate system we have the variable involved, such as we have x, y, z for Cartesian coordinate, r, phi, z for cylindrical coordinate, and r, theta, phi for spherical coordinate. So you have to know which coordinate system that you are using and what is the variable involved in your analysis. It's not all variable exist in one solution. Laplace equation is basically the homogeneous form of Poisson equation, where when we have a problem where the potential specified on conducting bodies, for example, when we have rho v is equal to 0, when we don't have the charge density inside our system, so the right hand side will become 0. This is what we call as a Laplace equation. This equation is very important to solve many problems related to the material. Okay.